next problem is called combination sum tree. We have to find all valid combination of k numbers that sum up to n such the following conditions are true. We can only choose numbers 1 to 9, and each number is used at most once. So we don't have repeating numbers, and we can only choose from 1 to 9. That's basically our set of candidates. We have to return a list of all possible valid combination, and the list must not contain the same combination twice, and the combination may be returned in any order. So we have to skip the duplicates, and the list can be returned in any order. So for example, we have K3 and we have N7, and we can choose the numbers 1 and 2 and 4. So we are choosing 3 numbers. They are all from 1 to 9, and they are summing up to number 7. Now for the second example, we have K equal 3 and then is equal to 9. So we have 1, 2, 6, which is 1 plus 2 is 3, plus 6 is 9. The same goes for 1, 3, and 5, and 2, 3, 4. So there are 3 valid combinations that we are returning. And in the last example, we have K is equal to 4 and N is equal to 1 because we cannot repeat numbers, and the numbers are from 1 to 9. We cannot have 1 plus 0 plus 0 plus 0 because this is first of all repeating numbers, and also 0 is not allowed as is not part of the candidate that we can choose. So there are no valid combinations. Now the K ranges from 2 to 9, and the N is basically from 1 to 60. Now, so there are a few restrictions that are actually making our problem easier. We can just use the logic that we have used for the combination sum 1, but for the set of candidates, we are using 1 and numbers 1 to 9, so that those are the only numbers that we can choose. We can use the start variable. So in our for loop in the helper function, we'll be starting from the start, not the 0, to prevent using the number multiple times. And because we are going in sorted order, 1 to 9 always, the array is already sorted, so there will be no duplicates. We don't have to worry about that. As always, we start with defining our list of all the combinations that we have managed to generate. We call our helper function and return the result. This is a common flow when we are dealing with backtracking problems. Now, for the helper function, we just propagate the k number of elements that we have to choose. That's the length of our combination, and is the number that that our combination, the elements that we have chosen for inside our combination have to sum up. The current sum is the current sum that has to match the n. Start is the index from where our each helper function is starting from. Current list is the list that is the combination that we are currently generating, and the result is the result that we propagated from the main function that we are returning as the final output. We first check if the current list size is larger than k. In that case, we can just return it because we are not considering the combinations that are larger and less than k, because we can only choose k elements. If the current sum is equal to n and the current list size is equal to k, then we have a valid combination, and we can just add it to the result and return from our function and go up in the recursion tree. We start from we implement a for loop, and we start from by declaring that I is equal to the start, so that we can control that each element is used once, because if we use the current element in the first call of the helper, it will not be possible to use it in the second one, because the start will be incremented by 1 in the previous call when we are calling the helper function recursively. Also, because the numbers are sorted, and the candidates are sorted, and there are no duplicates in the candidates. There are numbers just 1 to 9. We don't have to worry about the duplicates in the output list. We just check if the current sum plus the candidate that we are adding is still smaller or equal to the n. And if that's the case, we add the current candidate to our current combination, and we call the helper function recursively by adding the current candidate to the current sum, and also incrementing our start for the next call of the helper function. Finally, after we are done, we are back into this call of the function. We have to backtrack and we remove the element that has been added before we call the helper function. Now, for the time complexity, we have at most 9 choices, and the depth of the recursion tree is at most k. So we will have 9 to the k times the multiplier k, which corresponds to the maximum size of the current list that we are operating on, which is also our space complexity.